our discussion on flex sensor. Myself is Hitesh and I belongs to engineering physics third year. First, in this discussion we will cover introduction, working principle, circuit, basic circuit, and circuit design with signal conditioning unit, etc. Next, we will cover the general features and specifications, and also we cover types and applications of the flex sensor and the real part called errors, because this is not an ideal case like sensors and some of the error corrections that was done in the real life. And mm, this next is the differences part. This is the overview of the today's discussion on flex sensor. First, what is flex sensor? Flex sensor, as the name suggests, it will convert the mechanical bending energy into electrical energy, and that energy will be read by the signal conditioning unit, and it will give the measuring to the output devices. And basically this flex sensor will measure the deflection of bending on the surface that it was attached to. Next, how does this flex sensors work? The basic principle is, when there is a bending, due to the elastic property of the material, it will elongate as the length distance depends on the length, so distance of the flex sensor also increases. As the so there is a relation they are directly related to some extent. That property we are using to measure this bending to this bending. Here you can see first the flat case it was 25 kilo ohms, and when we measured that potential difference across that, get some value as the bend when it was bent into some angle, then resistance increases, so that the voltage across that also increases. So this is the working principle of the general basic flux sensor. Next, this is the basic circuit design. There is a constant resistor R and flex sensor resistance represented because it varies depending on bending. It, we measure the voltage of across this resistor 47 kilo ohms resistor. Due to the bending, the voltage across this R changes. So we can get the idea how we can indirectly measure the angle depending on the voltage drop across this R. And we will amplify using op-amps. We get the output in an amplified form, or we can change it into a current. This this is the general circuit diagram, and this is the practical use of flex sensor with along with Arduino Uno. This is the basic circuit shown here. The flex sensor and the resistor are here. This one is the resistor. We are measuring voltage drop across this resistor, small resistor. We'll get the idea about the bending in this flex sensor, and depending on that, we will do some extra works, like we will give some voltage drop to servo motor, or we will connect servo motor or some other motors and control that motors depending on the output voltage drop across we calculated, we measure. And these are the general features and specifications of the flex sensor that are available in the market. And the voltage range, working voltage range is 0 to 5 volts. They are usually low because generally we use it with Arduino, so the power rating will be, yeah, in between the range to suit with Arduino Uno. And temperature range can be this range. And when it was flat, it will have some general like 25 kilo ohms. It depends. It was general purpose flex sensor. It can be more, but this was general flex sensor that was available in the market. Resistance tolerance is 30%, and bending resistance range will, when the my like due to bending, it will change from 45 to 125. It's a maximum like when 180 degrees, it will have 125 kilohms. This is the dimensions of the flex sensor that was available in the market. These are the specifications, like it will have some resolution 0.1 degree. It can differentiate between or differentiate only when there is a difference between 0.1 degree differentiate. And repeatability plus or minus 3%. Accuracy can be plus or minus. This is the accurate error. And hysteresis, it depends on the elastic property of the material, so it will have some hysteresis losses. So it will be around 7%. And non-linearity, because the elastic property doesn't follow always straight lines, so there will be some plus minus 3 errors, 3% error. The and now we are going to discuss about the types. First one is the conductivity based flex sensor. Till now we are talking about this one. There are specifications and dimensions of this conductivity based flex sensor. These are the conductors, and this ink is the conductive ink. When there is a flux bending, the gap between these conductors increases, so the resistance increases. And this entire setup was mounted on a resin substrate, which is non-conductive. The resistance of the material changes because of the bending gap between the conductors increases. Thus, resistance increases. This is the conducting based flex sensor that was generally available in the market. And the other type is fiber optic flex sensor. This works on the principle when there is a bending, the amount of light reaches other end, it changes. When there is a flat, entire amount of light pass will be maximum. Due to bending, it will gradually decrease. So thus, if we measure the intensity of amount of light that was obtained at the detector level, on the other end, we can say the amount of angle it was bent. So this is the fiber optic flex sensor. Next is capacitive flex sensor, which works on the principle of capacitance. Due to bending, the capacitance of the capacitor will change. Thus, by measuring the change in the capacitance, we can measure the change in the angle or change in the angle of bending. And this is the velocity. This is similar to this conducting paste, but here this is the velocity which has a property due to bending or stretching. Its resistance will change. Resistance will be changed. Like the resistance will be decreased for this case. So here we can observe there is a gap between conductor. So when there is a pressure applied on this, it will be stretched, bending due to bending, and the resistance across this will be also changed because its resistance is changing due to bending. So thus, when we measure voltage across this thing, we can calculate the angle because both are linearly proportional to some extent. This is the typical. This is general matrix arrangement of this velocity single element. This is the velocity single element. This one representation, and this is the matrix arrangement of this velocity sensor, and you will get the voltage across this voltage drop across. We measure here terminals. And now we are moving to the applications. First application is human machine interface devices. Here in the picture she was wearing a glove which is called data glove. It will it's a sensor which has flex sensors, which will measure the bendings in the hip joints, and it will be sent to the signal conditioning unit. That unit will measure the things and amplify and change depending on the program it was programmed to. That's and it will reflect all of this in the virtual reality show hearing. This way, there is a connection between the real world hand gestures into the augmented world action. This is the first application. Second application is used to treat patients in the rehabilitation center to know the joints, joint movements, to record the joint movements. And we can also use it, as, use it to detect damages in the metastructures. Not all damages, but which are bending. We can we can record the movements of those bendings. Like if it was ideal case, then it will work. It will bend in a good amount. The bending will be good amount, and it can sustain the bending to some extent. And it can also recoil after release of the force. But if it was has some damage, then it can't recoil perfectly and it can't bend perfectly. So by studying the data, we can get an idea of is it damaged, or how much extent it can work. So in robotics, it is used with flex sensors are used to monitor the joints, how much bending is applied, and due to load how much bending it can store, and how the motors are performing at the joint level, etc. We can use it in the robotics also. For computer peripherals, also we can use that. And in the musical instruments, due to some, if we plug some string, there will be bending in the strings of instruments, and that bending can be analyzed by signal conditioning unit to produce certain frequency of sounds. For in the electrical instruments, we can use as bending can be used for the sounds in the electrical instruments. Now we are going to move for the errors. Because no device has no errors. Every device will have some errors because they are not ideal. They are the real world. Everything has some errors. So flex sensor will also have some errors. Generally, uh, flex sensors that are available in the market has around 11% to 20% of error. But there's a plot showing the height by length ratio. Here height nothing but length is this part, active length, height is this part. Height by length ratio is being plotted here. For different height by length ratio, we are plotting the data like sensor resistance and bending angle. As the H by L ratios decreases, H by L ratio decreases, it was the error is also decreasing. But every ratio has highest uh, highest error at the very least angles, and least error at the highest angles, and ratio increases, ratio decreases as ratio decreases. The error also decreases here. The error here we call is due to the elastic property, which is nothing but Young's modulus equal to stress by strain. So force by area times delta L by L, delta L by L. So as change in length also increases from, and after certain limit it doesn't follow this Young's modulus property, elastic property. So there will be some errors. And this is we are keeping height as a constant, and for different lengths we are checking we are plotting this sensor resistance and bending angle. As the as the length increases, the they are they are merging at the highest angle. As length increases, their error will also decreases. The ideal will be around this way. Ideal will be they are tending towards ideal nature as height length increases. Now, what are some practical corrections that are used in the prac- practical world? This is a flat one. This is the entire resistor. It was cut into a triangular shape this way. But this is the cutted one. This is the uncutted one. Cut it into triangular shape. And they plotted the curve. This is the unplotted one, black one. This uncutted one, uncutted one. It was following it into a curve shape, not the straight line. Straight line. But as the cutting ratio increases, it, this height and length ratio for the cutted one is as the height by length ratio decreases, it was following some linear curve, linear curve, but it also has some error in the low angle regions. But as it progress to higher angle bending angle, its resistance follows near to resistance. Resistance was linear. Resistance versus the angle was linear. Now these are the references that I used. Thank you.